Hi, welcome to this lecture on mathematical methods for biologists. We have been discussing probability distribution and statistics. The topic for today's discussion is normal distribution. In this lecture, we will answer what is this normal distribution, what is the functional form, how do we use it, etc., etc. So, to understand this, let us think of a typical situation that we would face in a lab or in real life, where we do some set of measurements and we have two quantities which we typically take, which is mean or the average and standard deviation. So, let us think of two quantities. The first quantity is mean or average, which denoted by x bar, and if from any experiment we would also measure standard deviation, which is denoted by sigma. So, if we have these two parameters, so if I do an experiment and specify only two parameters, which is the mean and the standard deviation, typically one would assume that other numbers are distributed around this mean value. So, if I say mean x bar is equal to 30, one would naively think that the other numbers are distributed around 30 with a deviation of the value sigma, whatever be given this, by this number sigma. So, imagine that if we typically says, that is what one would naively think. Very often what people assume that such distributions are normal distributions. So, what is a normal distribution? It is some distribution which is distributed symmetrically around the mean x bar value. So, let us plot this and understand the plot first. So, here first of all, this is here x. So, what you would have? You would have a variable x. So, something that you would measure, variable x. This is a continuous variable. What does that mean? Continuous variable would mean that some quantity which can take any value, not discrete values. For example, the height or the gene expression. It could be 3.1 micromolar, it could be any value, it need not be a discrete value. It's not like it's only not just like a number 1, 2, 3, 4. It could be 3.1, 3.7, 5.3, it could be a fraction. So, if you have continuous variable x and it has a mean x bar and standard deviation sigma, the assumption is that around this is my x bar, around this there is a symmetric distribution. So, around this either side this is symmetric. So, if I draw something like this. So, this is symmetric around the mean value. So, this is the mean x bar and this is symmetric around this x bar value. This kind of a distribution is what is normal distribution. So, first point is this is symmetric around the mean x bar, and it has a width. So, typically I could draw the same distribution symmetric around x bar in many different ways. So, I could draw this slightly differently. So, let us say I could draw something like this. This is also kind of symmetric around this, but this is different from this. The blue curve is different from the red curve. I could draw many curves which are symmetric around x bar, but now which of this curve will be decided is my distribution of our interest. So, sigma will decide this curve or this curve. So, both of this curve have same x bar, but this and this have different sigma standard deviation. So, that is something that we will understand as we go along, but the point is it is a curve which is symmetric around x bar. So, the mathematical expression for such normal distribution is the following. So, as we know, this normal distribution has, so the probability distribution is a function of two parameters. One is x bar and one is sigma. Only two parameters you have to know. If I specify these parameters, I can get a distribution. I can say this is, if you specify this parameter, I can get some function. And this is a function of this variable x, function of x. So basically, the probability distribution P would be decided by these two parameters x bar and sigma, and the variable is x. So now let us write the mathematical expression for this, which is as follows. So P of x, the probability to have any value around x given an x bar and a sigma is, it is a normal distribution, is a Gaussian function. So e power minus x bar whole square divided by 2 sigma square times some constant a. So this is the mathematical form. This is a normal distribution. So typical normal distribution is e power minus bx square, or so this is the Gaussian function. So the mathematical function called a Gaussian function, which has of the form e power minus bx square, or e power, so a e power minus bx square, or a e power minus b x minus x0 whole square. This is a typical functional form where b is like 1 by 2 sigma square. So here b is like 1 by 2 sigma square. So this is the functional form. Now what is a? So we would understand what is a means. Now let us make a statement for p. What precisely the p means? So the p means, so the p is nothing but probability density. Probability. Why do we call it probability density? Because the integral p of x given x bar and sigma, the integral of this with dx has to be 1. So this is called a normalization. The total probability, what does this mean? The total probability is 1. Therefore, since this integral is 1, this will have a, this is like, has a dimension, if x is a length, this will have a dimension of 1 over length. So depending on, this is, p is more like a probability density. This is more like something divided by x, so that you multiply with this, x will be a number. So this times this should be a number dimensionless. So this will have a dimension of 1 over x. P has a dimension of 1 over x. Only then p times x will be a dimensionless number. So this is important to remember. What is the meaning of p? The meaning of p is the probability to find the value of x. X as we just wrote. So I would just write p of x. The sum, of course, sigma and x bar is a part of it. So this is an exponential function, minus x bar whole square by 2 sigma square, and this a value here, which would be determined by this integral as we wrote, if this, we would choose an a value such that this p of x dx is 1. So we would choose an a value which would satisfy this condition. Now what is this p of x dx 1 actually mean? It is normalization, as we said, we used, as we use in every probability distribution. This is the normalization, so which says that essentially the total probability is 1. That's what is means. So what does p of x means? P of x means the probability to have a value x, around x between x and x plus dx. So now the total probability to get any value between minus infinity to infinity is essentially 1. Let us a little bit more think about this integral of this a little bit. So, let us plot the distribution first. So, this, let us plot a normal distribution. So, I have a distribution which is should be symmetric and nice. Now, if I just take this integral p of x dx, so this is p of x versus x, and this integral is equal to 1, would mean that the total area under this, the whole area under this is 1. So, if I just mark this whole region from minus infinity to infinity, this area is 1. That is what it means. So, the total probability, so this also physically means to probability to get any x value between minus infinity to infinity, this is minus infinity somewhere here, infinity here, is 1. You would surely find some of these x values between minus infinity and infinity. Now, if I take a small part here, which is a small region, let us take the same distribution and look at a small region. So, let us look at a region between this and this. So, this is A and this is B, and this area under this, area of this shaded region, mathematically will be essentially written as integral a to b p of x dx. So, this is the, if you do this integral, which is basically the area of this shaded region, and what does this mean? This essentially means probability to get any value between a and b, probability to have any value between a and b. So, if I have some data which is normally distributed, and the probability to have any value between a and b is basically shown or calculated by computing this area between a and b. So, this is important to remember. This means probability to have values between a and b, values between a and b. So, probability to have values between a and b is basically obtained by this area. So, this area gives the probability to have values between a and b in the distribution. So, let us take an example. Imagine that you have a bunch of cells. So, again let us go back to experiment. We have a bunch of cells, and let us say we are measuring the area of each of this cell, and if we plot this area p of a, that is what we are plotting, and the mean is a bar and the standard deviation is sigma. The expression for this p of a would be some constant, which I would write now here, normalization. So, it will be e power minus x bar whole square, here x is a, by 2 sigma square times some normalization constant, which turn out to be 1 by root pi sigma. Always this a, the normalization constant, will turn out to be 1 by root 2 pi sigma. This is the form of a, so this a is actually x. So, so if I have this measurement where I have lot of area data given, so I have a lot of area data, and from this area data I plot this distribution, which is a normal distribution, p of a versus a, and this is my a bar. So, let us say a bar is 100 micrometer square, and the probability to get very small area. What does this curve mean? This curve means probability to get very small area is small. Probability to get very large area is also very small. Probability to get area around this 100 micrometer square is very large. That's what this essentially means. Now, if I just look at this part alone, what does this mean? So let us say let me call this number as A1. A1 is this x axis number. The area corresponding to this line is A1. This area means, this area under this curve means probability to have the data above A1. Probability to have data, probability of getting values above A1. That's what this means. Now this could be x here, or area, instead of area you could have any other variable of your interest. It could be height, it could be size, it could be gene expression. So if the gene expression is in some unit m, let us say number of, if let us say you are measuring the amount of mRNA p of m, or it could be some protein level, all of this could have a normal distribution which could have a mean and a curve around this. So this is the first point one should remember, that this has this meaning, and the area means the value. So here this area would mean the probability to get values beyond this. That's what this means, and this is given by integral. So if this is, let me call this m1, so this integral is given by m1 to infinity p of m dm. If I do this, this would give me this area, and this has a meaning that the probability to get this number above this value m1. So that's what, and this is going to be very useful in understanding the normal distribution. Normal distribution has various uses. Where are we going to use this? When will a distribution be normal? So typically when you do an experiment, we cannot tell what the distribution would be. Would it be a normal distribution? Would it be some other distribution? Would be what would be the nature of the distribution? We cannot tell a priori before doing an experiment in most of the cases. So the variable that we are measuring, let it be area, let it be length, in some other case it could be some medical quantity, as we said, the distribution of vitamin D levels in a population. If we measure some quantities like this, we cannot tell what would be the distribution of this numbers that we get. But we can do one thing. We can say one thing about the mean, which is very often used in normal distribution. Whatever we measure, for example, let us say we do a survey and measure vitamin D levels of population in different pockets of different parts of a city or different parts of a country. So let us say so there are many people, 1,000 volunteers going around and measuring vitamin D level of people in different parts of the country. So let us say I am a volunteer. My job is to meet 100 people and measure their vitamin D levels. And so what I will have at the end of the day, so what are we doing? I am going to measure vitamin D levels of 100 persons. That's what I would do. At the end of the day, I will have data x1, x2, x3 up to and so on and so forth, x20 to 30, 40, x90, finally x100. So finally you will have x100. You will have 100 data points. So from this data point I can calculate an x bar, and of course a standard deviation also I can calculate. Now, if I have this x bar and the standard deviation, so I am volunteer 1. So I am volunteer 1 I have an X bar. Similarly, there are 1000 volunteers going around in different parts of the country. So let us say volunteer 1 gets each volunteer reports the mean value of vitamin D level of 100 people. So what I would have at the end of the day, if all the volunteers come together, the volunteer 1 would have X bar 1. The volunteer 2 would have an average value, which is a different average. A volunteer 3 will have another mean value, because this volunteer 3 met different set of people. So all of this all got from 100 persons. Similarly, there will be 1000 volunteers. So V 1000, 1000th volunteer will have a mean value X bar 1000. This is also got from 100 persons. So 1000 people went and met 100 individuals and collected the vitamin D levels from them, and each volunteer calculated a mean value. So we have 1000 mean values. Now we can plot the distribution of the mean values. That is, we can plot the distribution of the mean value itself. So P of X bar, we can do this, and it turns out that this always would be a normal distribution. So there is a theorem in mathematics which says the distribution of the means would be a normal distribution. This is called a central limit theorem. It is using central limit theorem, one can argue that if I do many experiments separately, and each experiment we could get the mean value of some n samples, if I collect all the mean values from different people and plot the distribution of the mean itself, that would be a normal distribution. Now how would we write a formula for the distribution of the means? So let me write here distribution of the mean values. Distribution of the mean values, I can write P of X bar. Of course, this also has to have a mean of the mean, so I would write X bar minus mu divided by 2 sigma square 1 by root 2 pi sigma. So this would be the distribution of the mean itself. Now this is important to remember. In this case, we don't know what is the distribution of the X. So this is, if I meet 100 individuals and measure vitamin D level, what is the distribution of the vitamin D level? I don't know. Irrespective of this, the distribution of the means would be a normal distribution. So this is the case where normal distribution automatically emerges. So whenever you have a set of measurements and you sum them and compute the mean, the result would be a normal distribution. So this is given to us, and this is something that is very surely a normal distribution. This is a case where we surely will get a normal distribution. Also to remember that whenever we have two variables, that is two parameters, which is mean and standard deviation, and if x is a continuous variable, then typically the distribution would be a normal distribution. Normal distribution is only two parameters, x bar and sigma, which is the mean and the standard deviation. One more thing to remember is what is the physical meaning of sigma. This is very important to remember. So if I have a normal distribution, this is my x bar. So if I have normal distribution, this is my x bar. What is the physical meaning of sigma? It turns out the sigma is the width. So this width is related to sigma. This width is related to sigma. So, but this width we can measure at different places. So where will we measure the width? I can measure the width here, or I can measure the width here. So if I measure the width of the distribution at some point, I would get the sigma. So let us think about measuring the width of this distribution. So the functional form that we have, so I would write the functional form, which is P of x is a e power minus x minus x bar by 2 sigma square. This is my normal distribution function. Now, if I measure the width at half of its peak, so when x equal to 0, of course, when x equal to x bar, this is 0, e power 0 is 1, and p of x will be a. So this would be my, when x equal to x bar, this is my a. If I measure the width at some point, half a, somewhere half the maximum. So if I measure the width at half maximum, so let me draw that here. I have this value is a. If I measure the width at a by 2, if I measure the width here, which is a by 2, so if p is a by 2, let us substitute a by 2 here. So what I would have, p is my a by 2. So a by 2 is a e power minus x bar whole square by 2 sigma square. So you would get this a cancels. I can take log on both sides. So log of half will be log of half on the left hand side, which will be log of e power minus something, which is minus x bar whole square by 2 sigma square. Now what is x minus x bar? This is x minus x bar. This is my x bar and this is my x. So x minus x bar is this. So half width is x minus x bar. So half width is x minus x bar. So x minus x bar is half width. So if I simplify this, what would I get? What I would get is that x minus x bar whole square is equal to log 2 sigma square. That's what I would get, 2 log 2 sigma square. This is my half width, so I would write w by 2 whole square is equal to 2 log 2 sigma square, which would mean that if I take everything to one side, what do I get? The full width, which is w square is 2 square, which is so 8 log 2 sigma square. In other words, sigma is w by 8 log 2. So this is root of this, of course, root of this. And this is what I would get. And one can calculate, if I know the full width at half maximum, so w is full width at half maximum. So if I know the full width at half maximum, I could get sigma by using this formula. So it's basically sigma is related to the width, and if I know the full width at half maximum, I can get this sigma. So to summarize, we have a distribution which has a mean and a standard deviation, and given this mean and standard deviation, we can construct a distribution which is called normal distribution typically, and this distribution has a few properties. Of course, peak at x bar, the mean, and it is symmetric, and the width is essentially the sigma, or width is related to sigma. And typically when you plot the distribution of the means, it will always be a normal distribution. These are the things to remember. With this, we will stop this lecture and continue in the next lecture.